All right, the last transcendental function I want to look at the antiderivative is the general exponential function, and you've got to remember the derivative in order to get to the integral. I'm going to cover this up down here. I'm giving it away, but I want to recall maybe how to derive that. I don't know if you remember how to derive the derivative of the general exponential function. I mean, we already know the basic one, right? This one here. If the base a is e, but the base a can be any number greater than 0 that's not equal to 1, right? That's any exponential function. What's the derivative of the general exponential function? Well, the way we do that is we actually realize that when I look at the expression e and raise it to the natural log of a, that I get a. Because remember, what is the natural log of a? It's the exponent, right? It's an exponent. Natural logarithms are exponents, and natural log is base e, so it's the exponent on the base e needed to get a. So if I take e and raise it to the natural log of a, I'm going to get a. Right? It's the power, natural log of a is the power on the base e needed to get a. So e to that power is a. This is the inverse relationship, right? If I plug a into the natural log function, get the output, then raise e to that power, I'm going to get back to a. Right? In a similar way, the natural log of e to the a is also a, right? We can use that inverse operation. But I'm going to use this one because I know this derivative already to take the derivative with respect to x of a to the x. And the way I'm going to do that is I'm going to replace a with e to the natural log of a. This is e to the natural log of a, all raised to the x power. All right, I've just replaced a with e to the natural log of a. But then when I'm raising an exponent to an exponent, what do we do with these exponents? Multiply. This is e to the x times the natural log of a. Now remember, the natural log of a is some constant. We're thinking of a as being some number, fixed number greater than 0, not equal to 1. So a could be 2 or 1/4 or pi or anything, right? Or even e for that matter. Okay, so it's just a constant times x. So when I take the derivative of e to this, it's the chain rule. I know the outer function is e to the u. What's the derivative of e to the u? Just e to the u. Look up above, right? So the chain rule says this is the derivative of the outer function, which is e to the u is just x times natural log of a, times the derivative with respect to x of the inner function. The inner function is x times the natural log of a. Now what is the derivative of x times the natural log of a? Natural log of a is just a constant. Think about what's the derivative of 2x? Answer 2. What's the derivative of 5x? 5. What's the derivative of 1/4 x? 1/4. What's the derivative of natural log of ax? Just the natural log of a. Natural log of a is a constant, so the derivative of natural log of a times x is the natural log of a. And so what do we have for our final answer? The derivative of a to the x is this times the natural log of a. But what is e to the x natural log of a? It's e to the natural log of a to the x power, which is just a to the x. So in other words, this is right back to what we started from, a to the x. And so what do we get for the derivative? Now I can reveal it, right? The derivative of a to the x is the natural log of a times a to the x. And notice that works for our general rule, because why? If a is equal to e, the natural log of e times e to the x. What's the natural log of e? What's the power of e needed to get e? 1, right? Natural log of e is 1. And so it does give us 1 e to the x. So this is the general rule. So now, though, I know what's the derivative of 2 to the x? Natural log of 2 times 2 to the x. But now the question is, what I want to know is, what's the antiderivative of a to the x? What's the antiderivative of a to the x? Okay, well, it can't just be just a to the x. We know the antiderivative of e to the x, obviously, is e to the x plus a constant, right? I mean, that's obvious. But how do we deal with this one? Well, it can't just be a to the x, because if I take the derivative of a to the x, I get the natural log of a times a to the x. What happened to that natural log of a? I've got to get rid of it. That's just a constant. And I can do that by simply what? Multiplying by the reciprocal, 1 over the natural log of a times a to the x plus c. Or I can write a to the x divided by natural log of a plus c. So now if I take the derivative of this function, I get a to the x. So there is the antiderivative of the general exponential functions. And of course, if this is e, this works because the natural log of e is just 1, so the integral of e to the x is e to the x. But what's the integral of 2 to the x? Well, it's 2 to the x divided by the natural log of 2. So for example, let's evaluate this definite integral now. What's the antiderivative of 4 to the x? It is 1 divided by the natural log, a in this case is 4, times what? 4 to the x. It's the so a is 4 in this case. Now I have to evaluate this thing at 1 and 0, so I've got 1 over the natural log of 4. Let me factor that out, and I'm left with 4 to the first power minus 4 to the 0 power. Of course, this is what? 4, and this is, of course, 1. I get 4 minus 1 is 3. 3 times 1 over the natural log of 4, or 3 divided by the natural log of 4. There's my answer. Remember, natural log of 4, this is really natural log of 4, right? So we're taking the natural log of 4. And that would be the exact answer. Now you can approximate it with your calculator, but this is what the answer should be. This is the exact answer. Okay. Let's do a couple more again. So just recognizing this form, trying to get it in the form. What do we need to choose for our u to get this integral into this form? Notice our variable this time is theta and not x. And so what do I see? I see 10 to the sine theta. So 10 to the sine theta times cosine theta. So what I need to choose, I need the variable to be the exponent. So I'm going to choose u to be sine theta. What's the derivative of sine theta? Cosine theta. Derivative of cosine theta is, sine theta is cosine theta. Du is cosine theta d theta. And there I see the cosine theta d theta. And so this integral becomes the integral of 10 to the sine theta, 10 to the u, and cosine theta d theta is just the du. Now it's in the form. You see, again, choosing this way of substituting. Again, I'm not choosing in this case, I'm choosing the inner function, technically 10 to the u, right, to be the u to be sine of theta, and I get it in the form I need it to be in. Instead of course, instead of x, I've got u, but the value of a is 10, so this is 1 over the natural log of 10 times 10 to the u plus a constant. Or if I want to write it this way, 10 to the u over natural log of 10 plus a constant. Okay. But the final answer is what? U is sine of theta. So in terms of the original variable, which is what I want, 10 to the sine of theta over the natural log of 10. Make sure you understand that's natural log of 10 plus c. That's the antiderivative. Pretty easy, but a little bit different than what we're maybe remembering about these general exponential functions. Okay. We'll finish off with one more. In this one, I've got a little recall from the previous set of lecture videos, right, on substitution. I showed you how to find the integral of tangent theta by basically writing it as what? Sine of theta over cosine theta, and choosing u to be cosine theta. And we get 1 over u, and the antiderivative becomes minus the natural log of absolute value of cosine theta, or the natural log of secant theta, because this -1 by properties of exponents can come up here as an exponent. Cosine to the -1 is 1 over cosine, which is secant. So either one is fine. But what I'm going to do now is, notice I've got a 7 to the x inside the tangent function. So I'm going to choose, I'm going to let u be the inner function. Okay. So what is the derivative of 7 to the x? So we just talked about the derivative of a to the x is natural log of a times a to the x. So that means the derivative is natural log of a, which in this case is 7, times 7 to the x. So du is this, du dx is this, so du times du is this times dx. Okay. Now if I look at what I have 7 to the x dx. Okay. Here I've got natural log of 7 times 7x dx. So if I multiply both sides by the reciprocal, 1 over the natural log of 7 du, then this is just 7 to the x dx. So that's what I'm going to replace with 7x dx, the 1 over natural log of 7 du. This is just a constant multiple, remember, and so my integral becomes 1 over the natural log of 7, pull that out, all right, integral tangent of 7 to the x is u du. And so from our previous lecture, we went through the process of finding this. And so this is going to be equal to this times 1 over the natural log of 7. So negative natural log absolute value cosine u plus c, which is equal to negative natural log of absolute value cosine, what was u again? U was 7 to the x. Okay. Again, you can also write this as the natural log of secant theta, and in that case your answer would be natural log absolute value of secant 7 to the x over the natural log of 7 plus c. So we can have either one of these answers. So you could see we get some strange looking functions, and you're going to get some strange looking functions as we combine these different transcendental functions and in different ways. There's compositions, and we're going to be looking at products and quotients a little bit later on when we look at techniques of integration with something called integration by parts. And so it is a little bit more of a challenge to find antiderivatives as opposed to finding derivatives, and you're beginning, I think, to see that. So you'll need to spend a little time looking at these examples, trying the ones in homework. They all don't look the same, but you can see where the u substitution is integral, very important to doing all of these integrals. Okay, very important to doing all these integrals. Okay, we'll stop there, and we will continue to explore how to find antiderivatives.